Alright, so I'm going to go through and do example problem 3-5, page 58 from the textbook. Those of you who were in class on Wednesday, you went through and you tried to decipher this problem from the textbook. And I'm going to go through and kind of hopefully give an overview that will make things a little clearer from that example problem. This was our first exposure to things being launched at an angle. We've previously looked at situations like this, where something is launched horizontally off of a cliff and falls due to only the force of gravity. In a situation like this, we were able to say that since the only force acting on the thing as it's flying through the air is the force of gravity, and the force of gravity is directed downwards, the acceleration of that object is also directed downwards. We took that a step further, and we were able to say that since the acceleration is only in the y direction, the horizontal velocity remains the same at each point, while the vertical velocity picks up in amount as time goes on due to the pull of gravity. We then talked about some concepts with this, namely the fact that it doesn't matter if the thing is being shot off at 20 meters per second or 10 meters per second, the time of flight is going to be exactly the same. In this case, it was 2.1 seconds, and if you run the video back, you'll see that it was 2.1 seconds when it was being shot with an initial speed of 20 meters per second. And we also determined the mass has nothing to do with the time of flight either. Even though the time of flights are the same, the distance horizontally that the object travels, that depends on the initial horizontal velocity, which makes sense. If it's in the air for the same amount of time, but it's going faster, it makes sense that it's going to be going farther. So we're going to kind of take this the next step, and rather than looking at things being fired horizontally off of a cliff, we're going to be looking at things being fired at an angle. And in this example problem, it says, oops, that was the wrong thing to bring up. In this example problem, it says that a football is kicked at an angle of 37 degrees with a velocity of 20 meters per second. It's a pretty high-tech football kicker who has these stats on his kick, but that's okay. We'll go with it. And I'm going to enter this information into this program. It says an angle of 37 degrees with an initial speed of 20 meters per second, and thankfully, there's even a football selection. I also could have selected bowling ball, baseball, adult human, but for right now, we'll go with football. Now, I'm going to fire this one time just to kind of see the trajectory that it's going to take. Football is kicked, flies around in a parabolic path. And since after the football is kicked, or in this case, launched out of the cannon, the only force that's acting on it is the force of gravity, because the air resistance switch is turned off. The acceleration of that object is going to be downwards. So we could say that this cannon has some initial velocity that's at an angle to the horizontal. Just like we did with forces, when things are at angles, we want to break that down into the horizontal as well as vertical components of the initial velocity. Now, horizontally, there's still no acceleration. Just like in the horizontal launch problems, the horizontal acceleration is the same at every single point along the flight. Make sure I'm drawing the same amount of arrows on either side. Same exact horizontal velocity, no matter where the football is along the flight, because acceleration is only downward due to the pull of gravity. The vertical velocity, which is initially upwards in what we'll call the positive y direction, that slows down and eventually comes to a stop at the very top. So at the very top of the football's flight, we can say that the velocity in the y direction equals 0 meters per second, because the football stops going upwards. Still has a horizontal velocity, but just stops going upwards, so it has no velocity in the y direction. Then, as time goes on, the football starts going downwards, So the y velocity starts increasing in the opposite direction. All right, so let's go through and we'll try and approach this sample problem. It says the football kicked at an angle of 37 degrees with a velocity of 20 meters per second. First thing I always do is I draw a useful picture or a diagram. Since this seems to be a motion problem, I'm going to draw kind of a motion map to help me understand what's going on here. And the motion map that I draw is going to be very similar to the figure 3-22 at the top of page 58. So I'll draw my ground, draw the initial velocity of the football, which is 20 meters per second. The trajectory of the football, we saw that it's going to kind of fly in a curved parabola. We know that anytime something is at an angle, we don't like that, so we can eventually split it up into the horizontal and vertical components of the initial velocity, or what I will call VO in the x direction and VO in the y direction. And just like we did before, as time goes on, there's no acceleration in the horizontal direction, so the initial x velocity stays the same at each spot. There is an acceleration in the y direction, so the y velocity decreases, and the speed in the y direction decreases until Vy equals 0 meters per second at the very, very top of the football's flight, and then it increases in speed in the opposite direction as it goes back downward. So this is the first thing I do. I should probably also denote what that means with the acceleration. Since only the force of gravity is pulling on the football as it's flying through the air, the acceleration is directed downwards. And this is the first thing I do when I start any problem such as this, is I draw my diagram to kind of help my brain think about what's going on in the problem. Now, the first question for part A, it says calculate the maximum height that the football goes. So part A is talking about the distance between here and here. Height is just distance, but in the y direction. So I'm going to start off by finding the components of this initial velocity, because when things are at an angle, we don't know how to deal with those, so we split them up into their components. If I draw my right triangle here, VOX, VOY, and I just took this and moved it over there. That's something you're allowed to do with vectors, and pick them up and put them down as long as you don't change the orientation. And VO equals 20 meters per second. We know that this is all at an angle of 37 degrees. VOY, that is the opposite side, so we can say that VOY equals VO times sine of the angle. VOX equals the initial velocity of 20 meters per second times the cosine of the angle. VOY equals 20 meters per second sine of 37 degrees, and that is equal to 12 meters per second for VOY. VOX equals 20 meters per second times the cosine of 37 degrees. VOY equals 16 meters per second. Now, the question didn't straight up ask us to do that, but it did imply that there was an initial velocity at an angle, and anytime there's something going on at an angle, components might be a helpful piece of information. So now that we have the components, let's take a look at part A. Part A wants to know the maximum height that the football travels. In other words, the distance from here to here, as I said a couple of minutes ago. In order to do this, that's a vertical height. So we probably want to list some information in the y direction. Remember, anytime we're doing an angled launch problem or a horizontal launch problem, we want to split things up into the x stuff and the y stuff, the horizontal stuff and the vertical stuff. In the y direction, we have an initial vertical velocity of what we just found to be 16 meters per second. We have an acceleration that's 9.8 meters per second squared due to the pull of gravity in the opposite direction of the initial velocity. We also know that this object, we'll say that it starts at the origin y equals 0 meters, and we are trying to find the maximum height to which this football goes. So I'm going to scan my reference table for an equation. Let's see, is there anything we missed out? Oh yeah, there's another super important piece of information that we missed there. Also, I said reference table, we don't get one of those. Sorry, I was in Regents mode for a second. The important piece of information that I missed is that the velocity at in the y direction is 0 meters per second at the top of the flight because the football stops going upwards. So now an equation that we can apply, and the book says this in the paragraph explaining part A, is the book lists this equation as Vy equals Vyo, I'm going to say Voy, or the original velocity in the y direction, plus At. Now, the book does some manipulation of variables before plugging numbers in, and I'm going to do the exact same thing. I think that's a very, very useful strategy. We know that the velocity in the y direction is 0 meters per second, so I'm just going to say that Vy is 0, so that means 0 equals Voy plus At. The acceleration there is not just any acceleration, but the acceleration due to gravity, which they wrote as g. I'm okay leaving that as a. That's perfectly fine with me. But I'm going to do a step of algebra, bringing Voy over to the other side, equals At. We're eventually trying to find the height, but for right now, we're going to first find the time and then use the time to find the height. So let's isolate time to get time by itself. Voy over the acceleration equals time. Plug in some numbers now that we have time by itself. Let's see, we got 16 meters per second for the initial y velocity over a negative 9.81 meters per second squared for the acceleration. Type that into my calculator really quickly, and I get a time of 1.22 seconds for the football to reach the top of its flight. In other words, the time right there at the top, time equals 1.22 seconds for the football to reach the top of its flight. So we did that. That's cool. I'm going to erase some of this stuff to get some more room. I'm going to add the fact that we know the time equals 1.22 seconds to our list of variables that we know about this point, the football at the very, very top of its flight. Now we want to find the distance. That's what we want to find, is the distance in the y direction, the height that the football goes. So we can apply another equation, y equals yo plus voyt plus 1/2 at squared, all these things in the y direction. We're trying to find the distance. Distance is already isolated by itself. We're good with that. We don't have to do any manipulation of variables. So let's plug some numbers in and see what we come up with. Y equals yo is 0, so that goes away. Voy is 16 meters per second. The time is 1.22 seconds. I'm going to run out of room here, so I'm going to write this down here. Plus 1/2 times our negative 9.81 meters per second squared of acceleration. I'm going to run out of room again. I apologize for that. Times 1.22 seconds squared. Again, all of this is in the book, so if my writing is kind of smushed there, I'm really just kind of going through and explaining what's going on in the book. But we got our height to be 7.35 meters. Cool. So that means we know that that football goes a total height of 7.35 meters. So I'm going to write that in there, that at the top, 7.35 meters. And I'm going to erase the stuff I just did so we can move on to the next part of the question. Okay. The next part of the question, part B, says the time of travel before the football hits the ground. Now, this is a completely level surface. And since this is a completely level surface, the amount of time that the football took to get to the top of the flight is the same amount of time it's going to take for the football to get back down to the ground. That only applies for level surfaces. In class, we'll look at some non-level surfaces, but for right now, since it takes the same amount of time to get to the top as it does to get back down to the ground, for part B, we know that that's just the 1.22 seconds to go up, plus another 1.22 seconds to come back down, so 2.44 seconds of total flight. I believe that the book has 2.45 seconds of total flight. I believe that they rounded something slightly differently than we did when we calculated the 1.22. Either one of them are completely legitimate solutions. So we can add that right there. Time equals 2.44 seconds. And then we can erase that. Move on to part C. Part C wants to know how far away the football hits the ground. In other words, it wants to know the distance from there to there. Now this distance is in the x direction. We're talking about x distance. So I'm going to kind of erase some of the stuff that we use for the y direction and list my x variables. The most important thing to do when doing problems like this is making sure that you keep your x stuff and your y stuff split up. You don't want to mix horizontal things with vertical things because you'll end up getting an incorrect answer. In this, we can say that the football starts at the origin at 0 meters. Not 0 meters per second, sorry, it's still early in the morning. 0 meters. We know that the initial velocity in the x direction of the football is 12 meters per second. We know that there is absolutely no acceleration in the x direction because gravity only pulls the football downward and air resistance is turned off. And we know that the total amount of time it takes the football to go from there to there is 2.44 seconds. 2.44 seconds. Let's see, at this point, I believe we can apply an equation because we want to know what the total x distance is. So we can say that x equals xo plus vo xt plus 1/2 at squared, the acceleration in the x direction. The x position is 0, so we can cross that off. We know what the initial velocity in the x direction is. We know what the time is for the football to fly the entire distance. We know that the acceleration in the x direction is 0, so we can cross off that entire term. That leaves us with x equals vo xt. We can plug in some numbers. X equals 12 meters per second for 2.44 seconds. Seconds cancel there. Let me do some math quick when I do that. Did I use the wrong velocity? Oh man, yes I did. All right, so I just caught myself that the initial velocity in the x direction, and thank you for catching me if you were playing along at home, the initial velocity in the x direction was 16 meters per second. Again, I did not do that on purpose, but this is good evidence about why you need to be extra careful about splitting up your x stuff and y stuff. Everything I said still applies. I just used a wrong number for the velocity in the x direction, probably because I didn't label my x variable very well over there. So the change I'm going to make right now is that the original velocity in the x direction is 16 meters per second rather than 12 because that was the horizontal component of the initial velocity. Then I can make that change down here. All right, that mistake didn't really hurt us very much, and I'm glad that I caught it. But the 16 meters per second times 2.44 seconds, that will give us a final position. Let me grab a calculator quickly. 39.2. 16 times 2.44. I got a final position of 39.04 meters, which is roughly what the textbook got. The textbook used 2.45 for the total amount of seconds because they rounded slightly differently than we did. I'm okay with 39.04 meters. So we know that the total distance the football travels is 39.04 meters. Cool. We can erase that. There's a lot of steps to this problem, so let's see what the next step is. That was part C. Part D wants to know the velocity vector at the maximum height. And that's where part D, this is kind of just a concept question. It just literally wants to know what is the amount of velocity at the maximum height? So we know at the maximum height, the velocity in the y direction stops happening. It stops going upward, so there is no velocity in the y direction. So that means that at the maximum height, the total velocity just equals the velocity in the x direction, which we know is a constant 16 meters per second. So in the x direction at the top of the flight, the total velocity of the football is 16 meters per second because there is no vertical velocity. It's all horizontal velocity. So part D. Part E, the acceleration vector at the maximum height. So again, part E is another concept type question, but since we drew our diagram so well, the diagram literally tells us the answer to part E. It tells us that the acceleration is directed downward at 9.8 meters per second squared because of the pull of gravity and the fact that the force of gravity is the only force that's acting on the football as it flies through the air. So now that we got this, let's test to see how close we were using this computer simulation. We got a distance of 39.04 meters that the football should fly. Let's see. We fired this football once. So let's bust out this tape measure. Measure from the base of the cannon to where the football lands. Got a distance of about 39 meters. That seems like it checks out. Go slowly through this example problem. Make sure that you're okay with the general approach that we took. It was basically the same thing as the horizontal launch problems where we split up X information and Y information, draw our motion map to help us. The one additional step of information that we need to do is split up the initial velocity into the X component and the Y component of the initial velocity. We can also sometimes apply the velocity in the Y direction equals 0 meters per second at the top of the flight. Look through the sample problem, go back, make sure you're good with this. On Friday, we will do a lab involving marble launchers. See you in class on Friday.